Then we can move on to Mjed. This will be the first of 3 presentations related to project discussing various methods to trigger secondary dissipation effects to slow down the debonding of composite substructures. Mjed will kick off in this discussion regarding a T-joint, which is a very commonly found substructure in aerospace engineering, among others. He recently defended his master thesis on this topic, and we're very glad that he decided to join us for his PhD as well. So he'll be continuing related research in the future. Go ahead, Mjed.
Thank you, Bram, for this kind introduction. Good afternoon, everyone. Today I'll be presenting my work on my master thesis work, which I completed last month, on laser-based pretreatment of secondary bonded composite T-joints for improved energy dissipation. 1 second, sorry. Okay. So as we know, composite materials are being widely used in the aerospace industry, mainly due to their high strength and high stiffness compared to low weight ratios. For example, if we look at the Boeing 787 Dreamliner aircraft, 50% of the aircraft is composed, 50% by weight is composed of advanced composites. However, inside the aircraft, there are other structural components inside the wing, for example, such as the ribs and the spars, which are still being used by, metallic materials. And these metallic materials often cost huge weight penalties and would often need to be connected by bolting and riveting, which can cause areas of high stress concentration. So as an initiative to employ more non-metallic materials and employ composite materials in the aerospace industry, many studies have been going on CFRP and composite T-joints, which consist of 2 laminated stiffeners bonded together to a skin using a special adhesive. However, the quality of the bonding determines the integrity and durability of these structures. So there are many toughening techniques, but my study focused on investigating a novel carbon dioxide laser pretreatment technique on the adherence of the CFRP T-joint to improve the toughness. I also wanted to understand the failure mechanism in toughened CFRP T-joints considering different surface ply orientations. So I had 4 different pretreatment techniques. The first one was a baseline peel ply pretreatment, and the other 3 were laser-based pretreatment. A low fluence laser cleaning, a high fluence laser ablation, and an alternative pattern between laser cleaning and laser ablation. For the stacking sequences we used, it was a quasi-isotropic stacking sequence, which had a 0-degree ply on the surface, on the surface of the ply. I also did 2 other tests on T-joints, which involved having a 45-degree ply orientation on the surface to understand if anything would change by having a 45-degree on the surface. So for the experimental methods, it was a simple manufacturing process, a hand lay up, where CFRP prepregs were laid up with the respective stacking sequence on a mold, and then the fixture was closed and the stiffeners were cured. The skins and the stiffeners were manufactured separately, and after they were cured, they have been bonded using special adhesive. They have been experienced laser treatment before being bonded by the adhesive. So the areas which were treated were the bottom of the stiffener and the top of the skin. And these were the areas of contact. So this is, for example, here what you would see from a patterning. It is the dark area is the laser ablation and the light area is the laser cleaning. After treating or after applying the laser irradiation on the surface of the adherents, they have been bonded using an Araldite 420 AB adhesive. And after curing, the specimens or the T-joints have been tested using what is known as a pull-off test, which simulates out-of-plane loading in real conditions. Initial results of the pretreatment show how the high fluence laser ablation actually evaporated or removed the full resin off the surface, and the fibers were fully exposed. We have also noticed that some fibers were cut due to the high temperature or the amount of heat that was transferred across the fibers. And another notice is that there is not much of a difference between the peel ply and the low fluence laser cleaning. However, when we put the laser cleaning next to the laser ablation, there is a change in the morphology between them. And this was further verified using a surface topology characterization. We can find a high change in in the height between the laser ablation region and the laser cleaning region. And we predict that this change can act as a reason or a barrier for cracks to propagate. As a reason for cracks to stop. So the mechanical results of the pull-off test showed how when we had the baseline peel-ply treated T-joints, catastrophic failure happened, while as we employed laser treatment, as we employed the laser pre-treatment, the toughness has increased. And the best toughness was achieved using the patterning, the B5G5, with having a 0-degree ply orientation on the surface. This actually resulted in improving the critical displacement by 4 times and improving the area under the curve, which is the energy dissipation, by 12 times. And this is the reason, so we took a video of the T-joint during failure, and we noticed that actually progressive failure happened where the crack started migrating up and down across the adhesive. And this resulted in the creation of what is known as adhesive ligaments, which Ran will talk about later in his presentation. But these adhesive ligaments actually were reasons for the improved toughness in the T-joint structures. So in conclusion, the laser pretreatment provided enhanced toughness and energy dissipation as compared to the peel-ply pretreatment. The laser patterning resulted in up to 12 times enhanced energy dissipation by the activation of non-local damage mechanisms. Progressive failure mode occurred for laser pattern T-joints, unlike the catastrophic failure which happened with the peel-ply treated T-joints, which indicates a safer T-joint with patterning. And also it is worth noticing that having a 45-degree surface ply orientation produced weaker toughness as compared to a 0-degree ply orientation, as the 45-degree ply orientation did not have the adhesive ligament phenomena which happened with the 0 ply. Thank you for your time, and let me know if you have any questions.
Thank you, Mjed. Azam has a question there. He asked the following. How about volume fraction of reinforcement and thickness of the laminate, and why did you select this type of stacking sequence?
Okay, so for the, sorry, can you repeat the first part of the question?
So he's curious about what volume fraction you used and what the thickness of the laminate was.
Okay, so the thickness of each ply was 0.25 millimeters. And we used 4 millimeter thickness, so 16 plies in the skin. And we used 2 millimeters, so 8 plies in each stiffener. For the reason why we chose the stacking sequence, this is based on the literature, and we realized that quasi-isotropic is one of the best stacking sequences used in T-joints.
Okay, thank you.